Module 7, Blockchain Platforms. Lecture 1, Overview of Platform Characteristics. In this lecture, we will cover the following topics. Introduction to blockchain platforms. Common characteristics of blockchain platforms. Improving blockchain platforms characteristics, introduction to optimization approaches. This lecture is part of Module 7, Blockchain Platforms. With this lecture, you're going to learn how to recognize and compare the popular characteristics of blockchain platforms. Describe the characteristics of different blockchain platforms. Explain the benefits and drawbacks of the characteristics of different blockchain platforms. Use this knowledge to search for the optimal blockchain platform concerning the defined use case. The minimum requirements for this lecture are: good knowledge of general blockchain concepts, familiarity with main consensus types and other motivational mechanisms, familiarity with smart contracts infrastructure. Introduction to blockchain platforms. A blockchain is a type of distributed ledger technology, DLT, that allows multiple parties to record transactions in a secure and verifiable way without the need for a central authority. A blockchain system comprises the underlying technologies that enable a blockchain network to operate. It includes the protocols and algorithms that govern how the network functions and how data is stored and validated on the network. The term blockchain protocol is often used interchangeably with blockchain system, as the protocol defines the rules and standards that govern the functioning of the blockchain network. A blockchain protocol specifies how the network will operate, including how transactions are processed and verified, how data is stored and secured, and other important aspects of the network, such as block creation, validation, and propagation rules. A blockchain network is a specific implementation of a blockchain system/protocol that has been set up for a particular use case or group of users. It is a decentralized, distributed network of nodes that operate on the blockchain system and use it to record and validate transactions. A blockchain platform consists of a specific blockchain network and all the tools and services that are needed to develop and operate applications on top of that network. This can include programming languages and libraries, cloud hosting services, and other tools that make it easier for developers to build and deploy blockchain-based applications. It also includes a governance framework, which refers to the set of rules, processes, and mechanisms put in place to manage and operate a blockchain network. This can include things like the decision-making processes for making changes to the network, the mechanisms for resolving disputes or conflicts, and the policies and procedures for managing the network and its participants. Blockchain platforms can differ from each other in many ways, including their design features and capabilities. Consensus mechanism. Blockchain projects employ different consensus mechanisms to reach an agreement on the state of the ledger and the validity of transactions. These mechanisms, such as proof of work, proof of stake, or practical Byzantine fault tolerance, can impact the blockchain platform's security, performance, and energy efficiency. Smart contract programming language. Some blockchain platforms allow developers to use blockchain-based programming languages like Solidity or general-purpose languages like Rust. The choice of language can affect the accessibility and availability of developers, as well as the potential for interoperability with other platforms. It is also important to note that some platforms do not support smart contracts and thus do not have smart contract programming languages. Transaction processing speed and scalability options. The performance and scalability of a blockchain platform can vary greatly depending on the design of the networks and the consensus algorithms used. Some platforms can handle a high volume of transactions per second, while others may be more limited in this regard. It is important to consider how a platform is scaling or plans to scale, whether through Layer 1 scaling, main chain scaling, or through Layer 2 scaling solutions. Decentralization may be sacrificed to achieve higher transaction processing speeds. Transaction types. Some blockchain platforms support only basic transactions, such as the transfer of tokens or assets, while others support more complex transactions, such as smart contract interactions or atomic swaps. The capabilities of the platform can affect the types of applications that can be built on it and the potential uses of the platform. Developer capabilities. Some blockchain platforms, more established, example, Ethereum, provide a wide range of tools and features to developers, such as libraries, frameworks, and services, that make it easier to build and deploy decentralized applications. Others may have more limited capabilities, requiring developers to build more functionality from scratch. The capabilities of the platform can affect the speed, cost, and complexity of developing applications on the platform. Permission model. Some blockchain platforms are permissionless, meaning anyone can participate in the network, validate transactions, and use services. Others are permissioned, meaning that access to the network and services is restricted to a specific group of participants. This can affect the security, scalability, and governance of the platform, as well as the potential uses of the platform. Level of decentralization and censorship resistance. Decentralization refers to the distribution of power and control among the participants in the network, and it can provide benefits in terms of security, fairness, and transparency. Censorship resistance, on the other hand, refers to the ability of the network to resist attempts to censor or control the flow of information or transactions on the network. For example, some platforms may be more centralized, with a small group of nodes or miners that control the majority of the network's resources and decision-making power. This can make the platform more efficient and scalable, but it may also make it more vulnerable to attacks and censorship. A blockchain system must enable 4 functional modules to perform as a decentralized, trusted data ledger and transaction processing system. The functional modules are settlement, consensus, data availability, and execution. Settlement guarantees that the committed transactions, batch, are valid and irreversible. Consensus ensures agreement among nodes on the content of new blocks being appended to the ledger. Data availability distributes the ledger data among the nodes in the network and makes the ledger data redundantly available. Execution is the trustworthy processing of the transactions according to the smart contract rules and updating the chain state accordingly. In a monolithic blockchain design, all 4 modules must be implemented in the same blockchain network. With modular design, the functions can be outsourced across specialized blockchain networks or chains. Blockchain network architecture is the way how a particular blockchain network is structured. A one-tier architecture keeps all the nodes, and thus all the functions, in a single layer, i.e., the one and only network, also called Layer 1 network, L1. The layered architecture comprises several layers, Layer 1 and sublayers, Layer 2, L2, Layer 3, L3, etc. The layers are interconnected to share data, security, and execution. The layered architecture enables the interoperability of various blockchain networks and performance scaling. With layered architecture and modular design, we can also spread the blockchain functions among specialized but interconnected networks to additionally improve performance and security. In this case, the layers are specialized for a specific function, example, to ensure only the execution of transactions or to provide security in settlement and consensus for other layers. Consortium, governance, licensing. A blockchain platform governance consortium is a group of individuals or organizations that come together to govern a blockchain platform. The goal of the consortium is to create a decentralized and transparent governance structure for the blockchain platform that promotes collaboration and decision-making among all stakeholders. The consortium typically includes a range of different stakeholders, including individuals, non-formal groups, institutions, formal organizations, private entities, and public entities. Some blockchain platforms are decentralized and not controlled by any single individual or organization and are therefore governed by the users or community who participate in the network. In these cases, there may not be a specific governance consortium, but the decisions and direction of the platform are still determined through collaboration and consensus among the stakeholders. On-chain governance models involve using the blockchain itself to facilitate decision-making and the implementation of proposed changes. This can take the form of stakeholder voting, where proposed changes to a blockchain network are decided by a vote of the project's stakeholders, who are usually holders of a governance token. Voting can happen on the blockchain itself, usually via smart contracts, and the results of the vote are automatically implemented if the proposal receives sufficient support. Off-chain governance models, on the other hand, involve making decisions and implementing changes through social discussion among the project's stakeholders rather than using the blockchain itself. This can take the form of decentralized discussions on forums, chat rooms, and social media, or it can involve a centralized management, consortium, board, or other decision-making body. In terms of blockchain software licensing, there are two main types, open source and proprietary. Open source blockchain software is licensed under a license that allows anyone to access, modify, and distribute the source code. This type of license promotes collaboration and transparency, and it enables anyone to contribute to the development of the software. On the other hand, proprietary blockchain software is owned by a single entity and is not available for others to access or modify. This type of software is typically developed and maintained by a single entity, and it may be sold or licensed to others for use. While proprietary software can offer certain advantages, such as the ability to control and monetize the technology, it may also be less transparent and collaborative than open-source software. Technology. Networking in blockchain systems refers to how the nodes or participants in a blockchain network communicate and share information. This is an essential aspect of blockchain technology, as it enables the decentralized and distributed nature of the technology. In a blockchain network, the nodes typically use a peer-to-peer, P2P, communication protocol to discover and connect with each other, distribute data and workload, and maintain the network's integrity. A blockchain node runs communication protocols such as low-level P2P network protocols for node discovery, network formation, flow control, or encryption of the traffic. High-level P2P communication protocols for node identity, session management, and data exchange between the nodes. Upper-layer protocols for exchanging data for synchronizing the chain among the nodes, example, block headers, and for exchanging transactions. It takes some time to propagate the information about, example, a new pending transaction or a newly mined block through the entire network and to reach all the network nodes. This network latency must be considered to ensure consensus on the blockchain state and agree on which transactions should be added to the ledger. The more nodes there are in the network, the more time it takes for the information to propagate the network. Despite being connected in the same network, nodes can have specialized roles. Full nodes keep a copy of the entire ledger. Validators or miners participate in the consensus process. Access node exports web-based APIs to enable off-chain application access to the network services. A node instance can be configured to have one or more roles. Block generation time is the time it takes for a new block to be created. New blocks are created by miners or validators, where in both cases, a validator or miner gets the chance to build and propose the next block. When the block is proposed, it gets propagated to other nodes, validators or miners, who need to confirm the validity of the new block. Because propagating and confirming takes time, the block generation time of a blockchain needs to be sufficiently long to allow for consensus to happen. Block generation times can vary from blockchain to blockchain. In general, it depends on the consensus mechanism used and the size and settings of the network. Finality can be defined as the moment when a transaction can no longer be altered. How and when a transaction achieves finality depends on the consensus mechanism, where transaction finality can be either probabilistic or deterministic. Only blockchains that can fork have probabilistic finalities. The transactions on these chains are never truly confirmed. Only the probability that a transaction can be altered becomes very low because the resources needed to alter the finalized transaction are too large. Forking is an event where a blockchain splits. It can happen when two blocks are produced at the same time. The system solves the problem so that the longest chain wins. Validators and miners on the network play a key role in determining which chain will be considered the longest and, therefore, the most valid. They do this by choosing which branch of the ledger to build on and by adding new blocks of transactions to the chosen branch. Since a transaction may be included in a shorter branch of the ledger that is ultimately discarded, transactions are not considered truly confirmed until a certain number of blocks have been added to the longest chain. This is because it becomes increasingly difficult to change or reverse a transaction as more blocks are added on top of it. As a result, users and applications should wait for a sufficient number of confirmations before considering a transaction to be final. Deterministic finality means that the transactions are considered final as soon as they are added to the blockchain. For this to happen, the majority of all validators need to confirm each new block before a new one is created. Latency, confirmation time, is the time it takes for a transaction to be confirmed. It impacts user experience when making transactions, value transactions, or interactions with smart contracts. Latency is correlated with the performance of the blockchain. With higher throughput, more transactions can be processed, no backlog. Consensus mechanisms allow nodes to agree on a single version of the truth, state of the ledger, without needing a trusted intermediary. Many protocols and incentives are implemented to ensure that nodes act honestly and agree on the ledger state. Achieving consensus gets hard with an increase in validator/miner nodes, which is why some consensus mechanisms require fewer nodes to achieve higher performance, high transaction throughput, fast finality. Many consensus mechanisms have been developed. We can divide them by the trust assumption they make to maintain consensus. Some consensus mechanisms require the assumption that all nodes are non-malicious, called non-Byzantine fault-tolerant mechanisms. They can be used only for permissioned blockchain platforms where all consensus node operators, validators, miners, must be known and non-malicious. These blockchains are only crash-tolerant, meaning that they are tolerant to nodes being disconnected, crashing, etc., but they cannot handle malicious actors. On the other side, we have Byzantine fault-tolerant mechanisms that can still achieve consensus even if there are malicious nodes on the network. Byzantine fault-tolerant consensus blockchains can be further divided by how the block producers are chosen, solving a computationally expensive puzzle or randomly selected, and how they get punished if they act maliciously, monetary punishment. For example, POW. Nodes need to solve a computationally intensive problem. The node that solves it first gets to produce a new block, as well as get monetary compensation for doing it. Nodes need to have expensive hardware and waste a lot of energy even to get the chance to produce a block. This increases the costs of an attack and makes it economically unviable. POS. Nodes need to lock up coins to become validators. Validators get randomly selected as block producers. Validators get their coin stake slashed to prevent bad behavior. This increases the punishment for an attack and makes it economically unviable. There are many other consensus mechanisms besides POW and POS, most of them being variations of POW and POS or hybrids. Some differences are in how block producers are chosen, proof of elapsed time, how validators are chosen/delegated, delegated proof of stake, proof of burn, how time is perceived, proof of history, etc. Some blockchain platforms support execution, computation capabilities, but some blockchains are designed for value transactions only, transferring coins/tokens. Execution refers to the ability of a blockchain platform to execute programs and perform computational tasks. Some blockchain platforms, such as Ethereum, support these capabilities, which allows them to support a wider range of applications beyond just value transactions. To allow the execution of code on top of a blockchain platform, a virtual machine, VM, which is run by all validating nodes, is needed. Without a VM, no smart contracts and, thus, decentralized applications are possible. While virtual machines, VMs, are used in many blockchain and distributed ledger, DL, technologies, there are some exceptions, such as Hyperledger Fabric. It is important to note that every transaction will alter the state of the blockchain. Besides value transactions, we also have transactions used to deploy or execute smart contracts, pieces of code. Smart contract deployment and execution transactions carry instructions that the VM interprets and executes. Because computation is expensive, every transaction is replicated and recomputed on every node. Transactions that deploy or execute a smart contract are more expensive. The immutable ledgers that document the complete history of all transactions in a blockchain are stored across many distributed nodes. The more nodes store the data, the more secure and resilient the platform will be. Data availability is needed because accessing the data is important for verification, replay transactions, and verify that they are correct. Besides storing pure transaction data, we can also store other kinds of data, photos, documents, etc., by embedding them in a transaction. There are two approaches to blockchain designs that affect how expensive the data storage will be. Monolithic approach: all data is stored on the main chain. This approach is very expensive because, usually, all data is stored across all nodes. Some platforms lower storing costs by storing data across a smaller group of nodes. These nodes are usually called permanodes. Another solution is data sharding, an approach where data is split into smaller parts. Nodes also get split, with each group of nodes taking care of one part of the data. Modular approach: data is stored on other specialized blockchains. For example, a blockchain platform could choose to forego data storing and only take care of processing transactions, and then writing all of the data on another blockchain. An example of a blockchain platform that is designed to provide data storage is Celestia. Other blockchain platforms can use Celestia as a data availability layer. In some cases, it is also possible to use cloud storage or other distributed storage systems, such as Interplanetary File System (IPFS). Using these solutions could be considered a modular approach, as it involves using external storage systems rather than storing the data directly on the ledger. However, it is important to carefully consider the security and availability implications of using external storage systems, as they may not provide the same level of protection as a fully decentralized ledger. Additionally, using external storage systems may require the use of additional protocols or systems to ensure the integrity and accessibility of the data on the ledger. In public networks, transaction fees apply when submitting transactions to the network. The transaction fee is used as rewards/tips for miners/validators. Processing and storage are expensive, waste a lot of resources, which is why transaction fees will be proportional to the number of resources needed. The transaction fee will be larger if a transaction is writing a lot of data on-chain or needs a lot of computing. Protecting the network from spam, DOS, attacks. Because every transaction comes with a cost, it gets too expensive to spam the network. Transaction fees are dynamic. In times of high congestion, miners/validators prioritize transactions with higher fees, larger profits. Some platforms, DAG-based ledgers or in consortium and private networks, choose not to have fees. Still, in that case, the DOS problem needs to be solved by either making users pay with their device's processing, solving puzzles, POW, or by having permission networks where all participants are known and non-malicious. Transaction fees can be lowered by scaling the performance of a blockchain platform. With the increase in performance, more transactions can be processed, meaning bottlenecks, backlogs of transactions, don't or rarely occur. If no backlogs are created, users are not competing on whose transaction will be confirmed first. Because the transactions in order execute systems, the majority of smart contract-capable networks, including Ethereum, are executed by smart contracts after the consensus. The smart contract code must be deterministic to ensure the finality of the execution. Many DL platforms limit the smart contract programming languages to only deterministic ones, example, Solidity, to avoid non-determinism. However, a deterministic programming language does not solve the problem of including non-deterministic data sources outside the chain and smart contract execution environment. The deterministic smart contract code is executed in a blockchain virtual machine. The execution is isolated from external, real-world environments, and the contract state is maintained and determined by actors inside the blockchain systems. Oracles are needed to integrate smart contracts with the real world. They collect and provide data feeds and input to smart contracts. The real world, in this case, implies external software, hardware, or human actors and the inputs they provide to be used in smart contracts. Software resources can be, example, web APIs from a weather data provider or real-time or historic price pairs for financial applications. Hardware resources could be an IoT sensor device, contributing sensory inputs, or physical device identifiers, example, RFID tag values, for a supply chain or a manufacturing management DApp. Human actors can provide inputs in the form of an answer to questions, their voting decisions, and alike. On the blockchain, oracles are represented by smart contracts that serve data requests by other smart contracts. There are two key trust models available to verify and validate the external data. In the centralized Oracle trust model, only one node is used by the Oracle solution to get data into a smart contract. Therefore, this node needs to be trusted. The alternative is the decentralized Oracle trust model. Here, the methods such as decentralized reputation, voting, or consensus-based decisions ensure a common agreement about the external data source. Some distributed ledger technologies, example, Hyperledger Fabric, apply a different transaction and smart contract execution lifecycle. The smart contract code in one of the nodes first executes a transaction, and later, the results of smart contract execution are validated against the endorsement policy. This makes access to non-deterministic external resources much easier. For more details on the execute order validate lifecycle and Hyperledger Fabric, see Module 7, Lecture 4. Most permissionless blockchain platforms do not support data privacy by default. User accounts may seem private because no personal data, name, email, etc., is shown, but in reality, accounts are pseudo-anonymous. Because transaction history is visible to anyone, and assets need to originate from somewhere, usually centralized exchanges, regulators could get information on who sends funds from the exchange address to an external address. Once a link to an address has been established, anyone can continue tracking where funds are sent or what activities, smart contract interactions a user has done. Links to an address can also be made by logging users' IP addresses, but this can be solved by using VPN services or running your own node instead of using third-party providers to access a network. With permissioned blockchains, private, consortium networks, all users usually need to be known, so there is no account privacy in such platforms. To preserve data privacy when writing data on a blockchain, users should first encrypt it because all transactions, and their data, are visible. Even though data and account privacy is usually not supported, some blockchain platforms have implemented privacy-preserving mechanisms/solutions. Privacy can be added directly on the main chain, called Layer 1, L1, or it can be inherited by secondary systems/chains to L1. L1 privacy can be achieved by building a blockchain platform that allows for transaction origin and destination obscuring. This can be achieved by using stealth addresses. The sender must create a new one-time address for every transaction sent. This allows the recipient only to publish one address, but all of the funds the recipient received are on different unique addresses. There are no links to the newly generated one-time addresses and the recipient's published address. Ring signatures can prevent transaction tracking by making it impossible to figure out who signed a specific transaction. Ring signatures are a cryptographic method where many users have a signing key. Any user can sign a transaction, making it very hard to figure out who among them has made the transaction. Zero-knowledge proofs, ZK proofs. Using ZK proofs, it is possible to prove something is true without revealing any additional information. This is why ZK proofs can be used to preserve the privacy of transactions by making sure that a transaction has been done correctly but without revealing the details of a transaction. Mixers. Using mixer smart contracts is another way privacy can be guaranteed. A smart contract can be written to mix funds from multiple people and then send the funds to their destination, making it very hard to trace the origin of each transaction. Smart contracts can also implement various cryptographic techniques, for example, ZK proofs. Layer 2 solutions can also provide privacy by offering users a separate privacy layer where all transactions are private. Permission networks are usually privacy-oriented by design, where the data can only be distributed among concerned parties. Participants cannot see the complete history of transactions like it is possible in most permissionless networks. Networks. A blockchain network is an incarnation of the selected DLT. We can implement various networks based on the same technology and differ only in, example, configuration details or the number of nodes in the network. Regardless of their common or diverse technology background, networks can adopt different approaches about who and how can participate in network control and operations, example, add nodes, share the ledger, participate in consensus, and use network services, example, create accounts, initiate transactions, use smart contracts. In truly public networks, anyone can participate in network operations, including the consensus, or utilize all the network services. In these networks, a high degree of distribution, i.e., many independent nodes, along with the BFT consensus eliminates malicious participants and ensures trust. In public networks, anyone can create accounts to send and receive transactions, hook to node APIs, or retrieve and share a copy of the ledger data. Only known selected consortium partners participate in network operations in a consortium network. Participation in, example, the consensus is limited and not possible for everyone. The network services can be limited to the consortium, registered users, or publicly available. Since the consortium partners are known and usually motivated to act honestly, the level of distribution in the network can be lower, and private networks are controlled by a single entity and are not really decentralized. Therefore, they should be used for testing purposes only. Unfortunately, some renowned blockchain networks that provide network services to unregistered users apply centralized control. Despite their centralized control, example, control of all the consensus nodes, they claim to be public. The trust in such a network is not based on decentralization but on the trust in the entity running it. Networks might, therefore, require permissions to participate in network control and service use. Only truly public blockchain networks are permissionless. Consortium networks are permissioned because the network control is limited to known consortium members. The network service access can still be permissionless or permissioned. In permission networks, the participants usually have a common goal but do not fully trust each other. Identification of the participants simplifies reaching the trust of the network. Apart from technical mechanisms in the network, example, legal agreements can be part of the control model and can be applied in case of disputes. Decentralization is the most important aspect of any blockchain platform, but it is important to differentiate decentralization from distribution. Decentralization refers to the distribution of power and decision-making authority away from a central authority and towards individual actors or smaller groups. In the context of blockchain, decentralization refers to the use of a distributed ledger technology, DLT, that allows multiple parties to maintain and update the ledger without the need for a central authority. This allows for greater autonomy, transparency, and resilience, as the network is not dependent on a single point of control. Distribution, on the other hand, refers to the physical or geographic distribution of something, such as data or computational resources, across a network. In the context of blockchain, distribution refers to the way in which the ledger, transactions, and other data are stored and managed across the network. A distributed ledger technology, DLT, allows for the ledger to be distributed across multiple nodes, which can be located in different physical locations. This allows for greater redundancy and security, as the data is not stored in a single location and can be accessed and verified by multiple parties. To achieve a trustless, secure, and reliable network, it has to be both decentralized and distributed. Together, decentralization and distribution provide the necessary conditions for a trustless, secure, and reliable network. Decentralization enables trustlessness by removing the need for a central authority, while distribution provides redundancy and security by storing the data across multiple nodes. Some platforms can be distributed but not decentralized, for example, private networks, where there is a central authority that takes care of updating the ledger. Other platforms may also sacrifice decentralization in order to improve the performance and scalability of the network. This can be seen by the fact that the network can only support a limited number of validators, which reduces the decentralization of the network. It is important to note that the validator nodes must be distributed and independent. If there are many validator nodes but they are controlled by a single party, the network is not truly decentralized. One problem of many blockchain platforms is excessively relying on third-party providers for running nodes, blockchain access, and web pages. It defeats the purpose of having a high number of independent nodes if a centralized system like AWS runs them. Similarly, the fact that most user wallets use third-party providers to gain access to the network and that many dApp web pages are run by centralized servers makes it much harder to maintain censorship resistance. The blockchain network is run by distributed nodes that run the software, protocols needed to operate the network. There are two types of upgrades that are possible on a blockchain network: client upgrades and protocol upgrades. Client upgrades, also known as software updates, involve changes to the software that runs on the nodes and implements the protocols. These upgrades may be necessary to improve the performance or security of the blockchain or to add new features and functionality. Unlike protocol upgrades, client upgrades do not lead to any forks in the blockchain. Protocol upgrades involve changes to the underlying rules and standards that govern how the blockchain operates, such as changes to the way transactions are processed or blocks are added to the blockchain. Protocol upgrades can sometimes lead to hard forks or soft forks, depending on the nature of the change and the extent to which it is supported by the network. Protocol upgrades are typically proposed and decided on through a process of governance, which varies depending on the specific blockchain platform. Hard and soft forks. A soft fork is a backward-compatible upgrade to a blockchain network. This means that the new version of the software is still able to process transactions made on the old version of the software. Soft forks typically involve changes to the network's rules intended to improve efficiency or security. A hard fork is a non-backward compatible upgrade to a blockchain network. This means that the new version of the software is not able to process transactions made on the old version of the software. Hard forks typically involve more significant changes to the network's protocol, such as changing the way transactions are processed or the way that data is stored on the blockchain. In some cases, a hard fork may result in a network split. This happens if not all nodes on the original network upgrade to the new version of the software. This can lead to two separate networks, each with its own set of rules and currency. The specific process for coordinating upgrades on a blockchain network can vary depending on the specific design of the network. In many cases, the network's users propose and vote on upgrades. This can involve a process of reaching a consensus among network participants, with the specific details of the upgrade being hashed out through a social discussion and sometimes on-chain voting. In some cases, an upgrade may be imposed by the network's developers, who may have the authority to make changes to the network's protocol without the approval of the network's users. This is more likely to happen with smaller, private blockchain networks, with fewer users and a more centralized decision-making process. Scaling and interoperability are two requirements often imposed on existing blockchain networks and systems. They have different motivations, but the approaches to solving one can help overcome the other, too. Scaling in blockchain can aim to increase the number of nodes in a network, thus, increasing the decentralization, distribute the ledger data among even more nodes for redundancy and trust, or scale the performance of a network. The key performance metrics are the number of transactions per time unit that a network can trustworthily incorporate on the ledger and the time needed, latency, to do so. Scaling should not come at the cost of security and trust. Performance scaling also directly affects transaction fees. Two performance scaling directions are present. Layer 1 scaling consists of making protocol changes like modifying block creation parameters, using different consensus mechanisms, using other data structures, or separating the chain into multiple smaller chains. Layer 2 scaling is made by processing transactions off the L1, usually using specialized blockchains that are more centralized but have higher transaction throughputs. Interoperability in blockchain refers to the ability of blockchains to communicate with other blockchains. The cross-chain interactions include messaging and token transfers. Interoperability solutions enable token swaps and bridges, native payments, or smart contract calls to and from diverse blockchain networks. These networks might share the same blockchain technology or rely on different ones. Besides bridges and swaps, the Cross-Chain Interoperability Protocol, CCIP, promises an open-source solution for cross-chain communication. For more information on scaling and interoperability, see Module 7, Lecture 2. dApps. A smart contract is a piece of code that is stored and executed on a blockchain platform. It specifies the rules and conditions for a particular agreement or transaction and automatically enforces those rules when the specified conditions are met. Smart contracts are typically written in a specific programming language that is tailored for use on the particular blockchain platform. Not all blockchain platforms support the use of smart contracts. Some platforms are designed only for value transfers, coin/token transfers, and do not have the capability to execute arbitrary code. Blockchain platforms that support smart contracts can be divided by the type of execution and languages they support. Most platforms only support deterministic execution, which means that the outcome of a particular piece of code will always be the same, given the same input. This is because the code is executed in a predictable, predetermined manner. An example of a deterministic language is Solidity, which is used to write smart contracts on the Ethereum platform. Deterministic execution is necessary in a blockchain because it ensures that all nodes in the network agree on the outcome of a particular piece of code, which is important for maintaining the integrity and consistency of the blockchain. Some blockchain platforms allow for non-deterministic execution, which means that the outcome of the code is not always the same. The main advantage of non-deterministic execution is that it allows for more flexibility and creativity in the design of the blockchain smart contracts, but may require a different and more complex validation procedure after the execution. Decentralized applications, dApps, are applications that are built on top of decentralized networks. These applications use the distributed nature of the underlying network to provide various benefits, such as increased security and resistance to censorship. Smart contracts are the key part of dApps. Smart contracts are used to automate various processes and enforce the terms of agreements between users. dApps, or decentralized applications, are web, mobile, and other types of applications that execute some or all of their business logic on a blockchain platform. This allows for trust in the recording and processing of transactions. Smart contracts are the trusted backend of this logic, and web and mobile applications, off-chain, that are connected to this backend, on-chain logic, provide the user interface and machine interface for interacting with users and other web applications. The backend part with the blockchain and smart contracts can be hidden from the user, and the user only sees the user interface of the off-chain application. This makes it possible to build decentralized applications that are easy to use and accessible to a wide range of users. The off-chain part of the dApp applications use web APIs to access blockchain services provided by the network. Blockchain platforms often provide client libraries to make it easier for developers to access the blockchain when building off-chain applications. This allows developers to focus on building the user interface and user experience of their applications without having to worry about the complexities of the underlying blockchain technology. Developers can even use already deployed smart contracts as their backend, where they can develop and deploy their own smart contracts. Blockchain scalability trilemma. 3 key properties define a blockchain network: decentralization, scalability, and security. Decentralization depends on the degree to which a blockchain network is distributed and governed without centralized authorities. Distribution is about the number of nodes in a network. The required computational, storage, or communication resources per participant might limit network participation and the distribution degree. Decentralization in a distributed system then depends on the governance of this system. In a truly decentralized blockchain network, anyone is allowed to participate in network control and operations, example, add nodes, share the ledger, participate in consensus, and use network services, example, create accounts, initiate transactions, use smart contracts. Scalability refers to the performance of a network, i.e., its ability to process many transactions. A scalable system must be able to process more transactions than its single node, and system performance grows with the size of the network. Security is the ability of a system to provide trust and show resistance to attacks or other malicious behaviors. Security can be ensured in a centralized way, i.e., in traditional banking or payment transaction systems. In these systems, we must trust the central authority. In distributed ledger systems, trust is achieved without a central authority by transparent data recording in a tamper-proof ledger and by cryptography and protocols to secure against attacks. The security of protocols in a decentralized system assumes distribution and decentralization of the network. Scalability trilemma states that not all three properties can be improved, simultaneously, and that trade-offs are needed among them. This is crucial for understanding the characteristics of particular blockchain networks. They sometimes highlight their strong points, example, performance scalability, but hesitate to reveal the trade-off made. Large public blockchain networks, example, Bitcoin, Ethereum, are decentralized and secure but struggle with performance, scalability. Conversely, Visa or MasterCard transaction systems are secure and very scalable. However, they are not decentralized. Consortium blockchain networks are less decentralized than public ones, but still more than a centralized system. Consortium blockchains thus aim to balance performance and decentralization. Layered blockchain architectures combine multiple ledger technologies. For example, optimistic rollups reduce the level of security in favor of performance. But the reduction here is planned and known and has foreseeable consequences. Thank you for listening to this lecture.